You may have heard of radiation or radioactive decay, but what's the difference between them and why do people say that they're bad? Well, in this video, I'm going to use some berries, like raspberries and blackberries, to demonstrate radioactive decay and talk a little bit about what is actually harmful about it. So, let's get started. The first thing we should get out of the way is that radiation is everywhere. Everything radiates in some form or another. I, right now, am radiating sound, as well as infrared light. A stove radiates heat. A flashlight radiates light. In this case, it's a UV flashlight. Now, some of this radiation doesn't really affect anything in the large scale. For example, when this flashlight is shined on my skin is not changing its chemistry. But there are some forms of radiation, like the radiation that would be created inside of a nuclear power plant, that can change the chemistry of things, and that becomes harmful. But those harmful kinds of radiation also come from a very specific source, called radioactive decay. So we're going to explore radioactive decay, starting with a simulation of an atom.
For this demonstration, we'll be referencing protons, neutrons, electrons, positrons, and gamma rays, which are essentially light. Now it's time to build the nucleus of our demonstration atom, which I'm calling barium. Light from a flashlight is radiated from the electrons around an atom as they move from one energy level to another. The more harmful form of radiation comes from the nucleus of the atom, as the nucleus changes in some way. So let's get rid of all those electrons.
Every time an atom or the nucleus of an atom undergoes some kind of change like this, it also radiates particles, and that becomes the radioactive decay that we're discussing. So let's go through each of these to see what change is actually resulting in what kind of particle and what happens.
One of the ways the nucleus of an atom can change is for one of the neutrons to just be kicked out of the nucleus. This is known as neutron radiation. But now the nucleus isn't balanced, so the protons and neutrons have to rearrange themselves, and in the process, they emit a gamma ray, known as gamma radiation. Another way for the nucleus to change is for one of the neutrons to just become a proton and an electron. The electron is high energy and shoots away from the nucleus, and this is called beta radiation, or beta decay. Yet again, the nucleus isn't balanced, and the protons and neutrons have to rearrange themselves and emit a gamma ray. Protons can also suddenly change, and they become a neutron and a positron. The positron is also high energy and shoots away from the nucleus. This is also known as beta radiation or beta decay because a positron and an electron are the same except for their charge. But the nucleus has to rearrange itself, and a gamma ray is ejected. Finally, a nucleus can change by having a whole chunk of it just fly off. In this case, it's an alpha particle, which is also just a helium nucleus of 2 protons and 2 neutrons. The alpha particle is also high energy and shoots away to make alpha radiation, or also this is referred to as alpha decay. You guessed it though, the nucleus is not balanced, but in this case, the nucleus tears apart and creates 2 entirely new elements.
So that's what radioactive decay is and where radiation, the bad kind of radiation, comes from. But what actually makes it bad? What's the big deal, right? Well, really there are 2 concerns of this kind of radiation. First of all, the particles that come off of this radioactive decay are pretty high energy, which means they can change the chemistry of things, like I mentioned before. They can also penetrate through certain kinds of material. So we can demonstrate that here as well.
A high-energy neutron can hit the nucleus of another atom and upset its balance. A high-energy electron can interact with the electron from another atom and essentially kick it right off. A high-energy positron could interact with the electron from a neighboring atom, but because they're the same particle essentially with a different charge, they annihilate one another. Now let's take a look at how deeply each one of these particles penetrate through material. In this apparatus, the top layer references some thin material like paper or human skin. The lower level is like several meters of lead. high energy gamma rays pass through things like paper, human skin, or even several feet of lead. Beta radiation, made up of electrons and positrons, pass through things like paper and human skin, but they do get stopped by several feet of lead. And alpha particles, although they are high energy when they start, are pretty massive, so they end up getting blocked pretty easily by things like paper or human skin.
So as you can see, with a moderate amount of shielding, we can actually protect ourselves from the radioactivity coming from radioactive decay. So then, why is it such a big deal? For example, you can stand next to a power plant and not feel the effects of radiation. Well, the problem is that there's always a concern that the actual atoms that decay might get inside your system somehow. If the nuclear power plant suffers some kind of a leak, or if waste material leaks into the surrounding environment, like the ground, it could get brought up by plants or animals, and eventually we could consume them or even breathe them in. And in that case, you have this particle that then radioactively decays inside you, and as a result, your internal chemistry starts to change. Slowly, but it does, which then leads to bigger health concerns. I hope this video answered your questions about radioactive decay and radiation and what really the difference is between them or why they're bad. If you liked it, don't forget to hit that like button, and also mention something in the comments about parts of it that you found interesting or questions you might have. Also, don't forget to subscribe for future content. Thanks.